everyone, welcome to the second part of our tutorial, Sparse Tensor Accelerator Abstraction and Modeling. I'm Nelly Wu from MIT, and I'm going to introduce our second part of the background lecture, which focuses more on the modeling perspective. Before we get started, let's have a quick recap on why do we care about sparse tensor algebra. As you can see in this figure, a lot of popular applications involve sparse tensors. These tensors can have density ranging from 10 to the negative 6 all the way to 100%. The zeros in these tensors introduce ineffectual computations, which are computations that involve zero. Because we all know that 0 times anything equals 0 and 0 plus anything equals anything, these computations can actually be eliminated because we already know the results. Let's take a look at an example application and see how much ineffectual computations can it have. We have a prune AlexNet plot. The y-axis is showing the density of the input activation and waste tensor. The x-axis is showing the layers. As you can see, for convolutional layer 4, both the input activation and waste tensor have density less than 40%. Thus, it has more than 80% of ineffectual work involved. Therefore, it is important for us to both understand how to process sparse tensor algebra on an accelerator design, and also how can we optimize these designs to exploit these ineffectual computation so that we can have better energy efficiency and processing speed. Okay, so first, let's take a look at how to process a default uncompressed sparse tensor workload on an accelerator design. Here we're showing a simple example workload, which is the dot product of two vectors a and b. The dimension here is named k, and what we're doing is essentially multiplying the corresponding entries in vector a and b and accumulate it to arrive at z. We also have a simple accelerator architecture with a one-level buffer and a multiply accumulation unit. In order for us to process this sparse tensor workload on the accelerator architecture, recall that we need something called mapping. Mapping defines the scheduling of data movement and compute in time and space. So as you can see here, we have a simple mapping which essentially points at the corresponding entry at each vector, do the multiplication and the accumulation. So how is this mapping realized on our architecture? Essentially, we will first store the vectors a and b in the buffer, and across time, we will access the corresponding entry like this. So in the time step 1, we are accessing the first entries in vector a and b according to the mapping, and these two values are sent to multiply accumulation unit to perform computation. And the computation here is essentially 0 times 0, and we also accumulate this value. Across time, we will be sending the corresponding entries in vector a and b to multiply accumulation unit to perform the multiply accumulation computation. As you probably have already noticed, all of these computations are very interesting because some of them are actually ineffectual, and there are a lot of opportunities for us to exploit because of these zero values in the computation and in the storage. Thus, ineffectual computations introduce a lot of opportunities for us to exploit as hardware designers. So what optimizations do people apply? We classify these hardware sparse optimization features into three high-level categories. The first one is what we call format. This refers to the choice of tensor representation. So we can actually choose tensor representations so that we can save the storage spaces by eliminating zeros, as well as saving the energy associated with these exercises. The second one is called gating. Gating refers to the explicit elimination of ineffectual storage accesses as well as compute. And by doing gating, we let the hardware unit stay idle for the cycle associated with the storage access or compute, so that no energy is spent. The third one is called skipping. Skipping, similar to gating, is also an explicit elimination of ineffectual storage accesses and computes. However, instead of letting the hardware stay idle and spend the cycle, skipping actually skips forward to save both energy and time. These sparse optimization features might look simple at a high level. However, there are various implementations associated with each other. As you can see here, we can ask a lot of questions in terms of how do we want to implement each sparse optimization feature. For example, what is the format you want to choose for a specific tensor? When do you actually want to perform the gate? Or when do you want to actually perform the skip? And also, there is a lot of interplay between the implementation that you choose for each sparse optimization feature. So, a lot of sparse tensor accelerator hardware has been proposed, and their hardware architecture are very diverse. So let's look at some examples here in the figure. You can already see that both the architecture topology and actually the sparse optimization applied are very different from one to another among these designs. Each of these designs carefully combines the sparse optimization feature that work the best with their architecture topology so that they can improve energy efficiency and processing time. It is very important for us to perform apple-to-apple comparison and also fast exploration of the designs in this diverse design space to realize new designs. And this is when a modeling framework can help us significantly. So we propose time loop V2, which is the focus of this part of the tutorial. Time loop V2 is an analytical sparse tensor accelerator modeling framework. It produces the energy efficiency and throughput of the design that you are interested in. It takes in several inputs. The first one is what we call workload. Workload includes the specification of the problem. For example, if you want to do matrix multiplication or convolution, it also defines an instance of the problem, such as the shape, for example, how many input channels and output channels there are in your workload. It also takes in the hardware specification. In our case, it's an architecture of the hardware. It defines the topology of your design, how many storage levels there are and how many computes there are. It also, for our purposes, defines the sparse optimization features applied to each component in our architecture. Another thing it takes in is the mapping, which defines how you want to map the workload to the architecture. And thus, time loop actually also tells us whether your mapping input is valid, because people can input invalid mappings so that these ones don't work on the architecture design. Let's take a look at first some validations on our proposed system. The first one is the validation on RSV1 Architecture, which is from ISCA 2016. We're showing a simple high-level architecture description here. As you can see, we have two global or shared storage. One is the DRAM, the other is the global buffer. Both of these storage store inputs, outputs, and weights. And we have a 168P array, which is 12 by 14, and each of the PE has its own local storage, each for one tensor that we're interested. So one input activation scratchpad, one output activation scratchpad, and a weight scratchpad. We're also showing an example mapping. As you can see, for a real architecture, the mapping can be really complicated because of the complexity involved in the architecture. And at a high level, these are the optimization features this architecture has. So you can see that we're compressing input activation and output activation at DRAM level. The color of these symbols is directly related to the tensor that the sparse optimization feature is applied on. And for the weight scratchpad, we're performing gating based on the inputs. We first validate on the DRAM compression ratio. As you can see in this table, we are comparing the results in the Aris paper to our analysis. For each layer of the convolutional layers in AlexNet, Aris is reporting the DRAM compression ratio, and as you can see, our work has a very close analysis result in terms of DRAM compression. We also compare another value presented in the RSV1 paper, which is a normalized energy consumption with sparse optimization applied. And since we're only applying the gating in the PE architecture, as you can see in the previous slide, we are comparing the savings of the PE. The paper says the PE saves 45% and our optimization shows 43%, which is very close to the ground truth. We also performed another validation on a SCNN architecture, which is published in ISCA 2017. And here we're showing a high-level architecture again of the design. SCN has more storage levels because they don't store weights and input-output at the same storage. So we have the input-output DRAM, which stores input activation and output activation. We have the WDRAM, which stores the weights and output activation as RAM is on chip. We have 64 PE in the array. Each PE again has the local storage for the input activation, the weights, and output activation. On the right, we're showing another example mapping, which is mapping AlexNet Layer 3 to the SCN architecture. Again, you can see there is a lot of complexity involved in the data flow. In terms of sparse optimization feature, there are a lot of compression involved in this architecture because it focuses on the sparse workloads. So both the input activation, output activation, and weights are compressed for the shared levels, and for the storage in the PE, the input activation and weights are compressed, and we are performing skipping optimization for 2 of the storage levels. Here we're showing the validation on the runtime activity counts. On the axis, we're showing the various components in the SCN architecture. As you can see, there is DRAM, there is the on-chip buffer, the IA RAM, and the back y-axis is showing the runtime activity counts error. So as you can see, we have less than 1% error comparing to the results generated by custom SCN simulators on all of these example layers that we run experiment on. So our framework is able to produce an accurate enough analysis comparing to the ground truth for SCN architecture.